Good evening, everybody. This is Obi-Wan Pez for Simplex Pachinko. Gonna be doing some math stuff tonight, so if anybody has any questions, feel free to drop stuff in chat, and we will get to it as soon as we can. So hope you all are having a good week so far. My second child is in a musical camp this week, so having some fun there. And first child is off, so we're having some fun time. She and I get to go on long walks around town. Oops. Don't run over the cable. This morning we went for a 5-mile walk. Don't regret it. 26 stacks. Yep, 2.5 up, 2.5 back. So how was calculus made easy? With the American pronunciation. Okay. That's fair. So far, is it coming up with some ideas of, or interesting ideas? Sure. If you can describe for me what that is for a second. I mean, I don't have necessarily an explicit idea of what it is. I probably understand the concept, but Hmm. Oh. Hey. You know what, let's open that on the other computer where I'm not streaming from. Preface to the second edition, October 1914. Yes, it did open. I will say I'm not 100% sure that this will not yell at me again and be like, oh, you've logged out, but, Okay, on degrees of smallness, page 3. Uh-oh. I may have waited too long to pull... there we go. The stylus has these little nubs, and over time, naturally, they wear down because this is scratching against the surface of the tablet. I was worried I waited too long to replace it. Excellent. Okay. Right, okay, so they're trying to get at the fact that over mathematical history, what has happened is that we've started shifting our focus from, relevant time intervals, from being days or years or months, to now sometimes using, minutes or seconds or fractions of a second, and having to come up with ways in which we can measure these lengths of time accurately, or precisely, whichever. Because they do sometimes, in fact, right? They do sometimes actually matter. Our forefathers considered it small as compared with an hour and called it 1 minute, meaning a minute fraction, namely 1/60th of an hour. Right, and needing such small subdivisions of time to be measured was thought unheard of at one point. In the 1600s, during Queen Elizabeth's days, they were called, each what we now call seconds were called seconde minute, or second order of minuteness. And we just call them seconds. Yeah. Farthings compared to sovereigns, yes, yes. The horrible monetary measurements of the UK, yeah. But, you know, they at least give you the point, is that a farthing compared to a sovereign is barely more than 1/1000th. And, you know, you could find the actual conversion factors online if you really wanted to know, like, how much each of these things was worth. But, yeah, penny farthing is the tiny amount of money. Uh-huh. That's fair. Okay. So, okay. So you have what are called differentials. And these things usually come in the form of dx, dy, dz, du, dA, and we could go on. Whatever variable you have, you stick a d in front of it, it just means that it's a small amount. So it depends on what you're talking about. I will say that most of this is probably a little bit outmoded, and we don't really talk about it that much. However, right, so usually we say that these things themselves are arbitrarily small. And, right, what do we mean by that? Well, it means that, like, no matter what you do with this thing, it's not going to affect the overall result at the end. So when you talk about something that is arbitrarily small, we're talking like, you know, they're trying to justify it in some of the other parts here as, you know, what is the old adage of what is a dollar to a billionaire, right? If Bill Gates drops $1,000 on the ground, is it even worth his time to bend over and pick it up? I think the answer is no, actually. But again, it all depends on what it is that you're talking about. So generally speaking, in a lot of the calculus stuff that you see later, what we do is we say, okay, if you're going to create a function and this comes way later. We do talk about it a bit in differential calculus, naturally, because this is what differentials are all about. How do you create differentials and all that? I'll get to it in a second. But in integral calculus, one of the things that we do is we create a slice out of a particular function in order to find out what the area is under this whole curve. So we create basically what's known as a representative sample here. Blandlin, I'll do my best to look it up. So what we have here is a rectangle which is representing a small area, a small slice taken out of this particular function. If we allow dx to be an infinitesimally or arbitrarily small distance away from a, or to be an arbitrarily small distance taken starting at a and moving to the right some. We could also say that like this right side here would be at x equals a plus dx. Overall, what we're saying is that that distance between those two things is so tiny that we could think of this as something that's like not even necessarily there. It could be essentially this thin, and we would be perfectly happy to say that the math works out the same. Okay. So oftentimes what happened was Newton started looking at what would happen if we took a function like this. Right. Yeah, if we looked at something like zoomed in a bit or zoomed out a bit, it should look identical realistically if we just make dx smaller or larger depending on what our needs are. So originally Newton was trying to figure out some bits of physics. And he said that what he needed was to figure out what the velocity at a particular moment would be. So we have ways of calculating the speed of, for instance, your car. If you look down at your speedometer, that is not actually an accurate, well, it might be accurate, but it is not an entirely accurate representation of how fast your car is going at that moment. And this is especially true if your car is accelerating in any particular direction. It's not necessarily going to give you a 100% accurate value. Now, these days, with the advent of digital instruments inside of your car, it does tend to work out very nicely that, you know, your speedometer is being updated 10 times a second or something like that. So, like, it's fine. You're not going to get an inaccurate reading off of that. But, you know, going back to my original car, a 1988 Plymouth Reliant station wagon with a very manual speedometer, I never quite topped it out at 85. Got pretty close once. But at that point, the car was almost shaking itself apart, so... Alright, let me grab this thing here. Let's see. I was gonna grab something. Yep, now I lost it. Okay, cool. Okay, so it was a terrible idea. So Newton, at various points, was looking at solving some physics problems where he was trying to find the speed of an object at a particular moment in time. And he noticed that when you were looking at a position function, so this is our position function, s. Now let's do x. X of t. Right, x is going to be our distance from 0. T is going to be time after t equals 0. Whatever that's going to be. So one of the things that we can do is look at this and say, hey, if we have two distinguishable points that are on this particular parabola, in this case, what we have is a t1 x1 and a t2 x2. Now what we have is time in seconds, and x is going to be a distance in meters, let's say. And we have the same over here. So we have distance function over time, and what we want is a speed, velocity, whatever we're doing. Right, at t1. So Newton, being the genius that he was. Now keep in mind, right, we are 400 years removed from Newton. Some of this stuff tends to be a little obvious because we teach it to elementary school students. Okay, but this was like hard mathematical research 400 years ago. So if you don't get it, don't feel bad. Or at least don't get it immediately. Eventually you'll get it. So what we have is a distance function given over a certain amount of time. What we want is a speed or velocity at t1. So what we find is that this is going to get us, speed or velocity needs to be talked about in terms of, in this particular case, units, meters per second. Well, if we just go and say, okay, well, it's like x1 meters over t1 seconds, that's a meters per second. But the problem is that doesn't really tell us what's happening. That is still telling us, compared to some zero value, compared to literally the origin point, right? Compared to the origin point, where's this thing? But that's not what we want, right? This is not going to go through the origin at any particular point. It has nothing to do with the origin. So we can't just do x1 over t1. And again, if you wanted to check, you could actually see here, okay, this is a negative time and a positive x. So our meters per second in that particular case would be negative. But if we think about what's happening at the moment that we're talking about here, right? At this particular moment, what we have is that as our time increases, and this is something important from pre-calc, as our time increases, our distance is also going to increase. So this should be getting us a positive speed, right? As our time increases, our distance increases, so our speed should be positive. So if we start thinking about it as just like x1 over t1, well, again, that's going to get us a negative value, a positive x and a negative t. That doesn't make any sense. Because again, that's actually comparing this particular place, t1, x1, with 0, 0. And if we were to compare that, you'll notice that here, that has a negative slope. Okay. Well, enough giving that completely away. But what happens here is that we notice that t1x1 and t2x2 have, again, a certain distance that has been traveled and a certain time that has been traveled through. So here, if we want to talk about, okay, well, this is not going to be an accurate measurement of the, this is not going to be an accurate measurement of the speed at t1, x1, but you know what? It's going to get us what we call an average velocity or an average speed that goes from t1, x1 to t2, x2. So here, instead of, let me do this, instead of just having t1 or x1 over t1, what we have to do is say, okay, we need to talk about this in terms of the distance that has been traveled from one point to the next and the time that has been traveled through from one point to the next. When we subtract two distances from each other, it's meters minus meters, you still get meters. So that'll work. And then seconds minus seconds, you still get seconds. And you know this from Algebra 1. Right, x2 minus x1 over t2 minus t1. This is going to be our average velocity, often listed as v bar. Average speed, average velocity. Velocity just means, again, that we're going to have a direction that's included in all of this. So for what we're doing, we're going to be talking about this in terms of up is a positive direction and down is a negative direction. Makes it a little bit easier. All right, so with our average velocity here, x2 minus x1 over t2 minus t1, we're going to show that this ends up, again, showing us the distance that's traveled in each of these dimensions. So t2 minus t1 is the distance traveled in the horizontal, in this particular case, t. And x2 minus x1 is the distance traveled in the distance direction. Vertical direction. Okay. So now with that, we say, okay, so how do we get a more accurate sense of what our average velocity is going to be, or a more accurate sense of what the actual velocity is going to be at t1x1? Okay, well, it gets to be, again, a little bit difficult to talk about because, yeah, you know, we still don't have the tool for it yet. So the genius of Isaac Newton was that he thought, hey, wait, if we take this and we now shorten the distance, go here to t3, x3, we shorten the distance between these points. We take a more recent measurement, right? A smaller sample rate, or faster sample rate. T3X3 is going to have a much more accurate representation of what our velocity is going to be at this particular point here. Again, it's still not 100% accurate, but it's actually a lot closer than what we had here for this slope. So for our average velocity, again, we're using the slope equation. Between 2 points. And this is also, by the way, what your car is doing, digital or mechanical. It has a sample rate, and it's trying to take readings once every so often in order to tell you what the average velocity is between those two moments. Now with the mechanical speedometer, it's a little bit different, blah, 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 etc. But it tries to make sure that there's an accurate sample. It doesn't necessarily work over, practically instantaneous time speeds. And if you were to hit the brakes really fast, all of the mechanics don't work 100% instantaneously. There's a delay to it. And it may also be an average velocity with a fairly small sample rate, but still it's going to count like an average velocity. Alright, so now what we can do is, instead of doing this one at a time, because that's super boring, what we can do instead is say that this distance here is just arbitrarily going to be called dt. And this distance here is just arbitrarily going to be called dx. So as our T3X3 approaches T1X1, our average velocity is going to end up becoming dx over dt. Now, in terms of differentials, this is all very well and good. Okay, which is again x3 minus x1 over t3 minus t1 or, here's the kicker, we could take T3X3 and instead of using those particular letters, what we do is we say, okay, our v bar here, or dx dt, is going to be equal to x3 is the same as x1 plus dx. Minus x1. T3 is going to end up being t1 plus dt minus t1. Okay, so now we can see that, yeah, okay, the x1 minus x1, the t1 minus t1 are going to just subtract out and you get dx over dt. Sure, but there's something else that you can do. and that is you can rewrite the x function. So instead of having all of this, we can say, okay, what we're doing here is we're saying that x1 plus dx is going to come about because what we do is we take the x function and we plug into it t1 plus dt minus x at t1. Okay, let me know if this is freaking you out any. So again, we take this x1 plus dx and instead reframe it as the x function where we plug in this t value. t1 plus dt. And then we take x1 and we just let it be x at t1, which is our t value down here. And then with t1 and minus t1 in the denominator, we can just let that go away, and we're just left with dt at the bottom. A bit is fair. Again, 400 years ago, this was cutting-edge research that like nobody understood except Newton himself. And that's maybe a little unfair. People sort of got it, but they weren't, you know, when it first came out, they were like, oh, okay, it makes some sense. Alright, so depending on the kind of function that you have here, whatever x is, our distance function, it's going to do different kinds of things. Alright, so generally speaking, and I want this to be generally, so we're going to knock this out here in a second. Right, the slope of the secant line. Now, whenever you talk about secant lines, this is not the trigonometric function secant, but rather this is saying like you have a curve, it's a line that goes through it. So it's got to hit it at least twice. Or if you're just talking like a curve like this, then you know, a secant line will go through it like that. You're more likely to see it like this. And within the modern era, you're probably more likely to see no dx's at all, but like an h or a delta x or something like that. to say that this is a change in our x value. This is a small amount that we have changed x. So if we wanted to do this real quick, right, let's assume that x of t is negative 6t squared plus 12t plus 7. Right, so this is not particularly going to like factor or do anything nicely. It's just a random quadratic that I made for this. Right, so then, that'll work. Let's say here that, that might be too big. It's fine, whatever. Let's say, for instance, that we want T1 x1 is going to be negative 1/4, comma, whatever this is going to end up being. So negative 1/4 squared is going to be negative or positive 1/16 times negative 6. 6/16 is going to be 3/8. Negative 3/8. All right, negative 1/4 times 12 is going to be a negative 3, and then we get plus 7. This is going to be 4 minus 3/8. So it's 3 and 5/8. So 29/8. Okay, T2, X2, we'll have this be, where is the vertex? It doesn't really matter, so we'll just let it be 1. Alright, so that's going to be 12 plus 7 is 19, minus 6 is going to be 13. Alright, so the slope of the secant of this particular setup, our average velocity, v bar, is going to be equal to. So here we have 13 minus 29/8 divided by 1 minus negative 1/4. So 1 minus negative 1/4 is going to be 5/4. 29/8, 8 times 13 is going to be 8104. So 104 minus 29 is going to be minus 30. Wow, okay. 74 plus 1 is going to be 75. 75/8. Alright, if we multiply both top and bottom by 8 would be convenient. Makes 75 over 10 or 7.5 meters per second. Alright, so that is the average velocity between negative 1/4 of a second. Seems kind of silly to say that out loud, but whatever, it's fine. Negative 1/4 of a second out to 1 second. So the average rate of change, the average velocity, 7.5 meters per second. And we can do that here with anything that we want. So we could say that our slope of the secant line could be equal to, here we have f of x plus dx. Okay, well, our f from up above was negative 6t squared plus 12t plus 7. I'm putting that way over there for a reason. Oh, yeah, that'll work. Okay, and then over here on the left side, we need to plug in x plus, t plus dt into our function up above. So function composition, again, pre-calc. This is going to say we take our negative 6. Instead of t squared, this is now going to be t plus dt parentheses squared plus 12 t plus dt. Oh dear. Yeah, not enough space. Let's move that over a bit. Okay, plus 7 minus parentheses the original function. Okay, so this is where you start getting into the degrees of smallness bit that they were talking about. So here we look at this and we say, okay, this is going to be negative 6 multiplied by t plus dt, and we're squaring it, becomes t squared. So whatever t is, no matter what number it is, this is a significant number, right? So it's negative a quarter, it's 1, it's 10, it's whatever you want it to be. It's going to be a number. And whatever number that is, it's going to be fairly decent size. And we're squaring it, so it's becoming also a bit larger. If it is a small number, it becomes smaller. But it is much, 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 much larger than dt. dt is an infinitesimally small number, in theory. It's just, in general, we call it like the deviation, right? It's our differential, the amount we have changed t. So in a lot of our calculus stuff, we want it to change by an infinitesimal amount. We're just saying that it's going to be this like tiny, tiny thing. For the moment, we can actually let dt be whatever we feel like. So if you want it to be a deviation of like 6 seconds, you could do that. It'd be really big. And it would matter significantly. So in this particular example, right, it sort of depends. All right, anyway, when you square t plus dt, we end up with t squared plus 2t dt plus dt squared plus 12t plus 12 dt plus 7. Okay, minus negative 6t squared, so that's a plus 6t squared, minus 12t minus 7. Yikes. Did you all see that? Psh, the audacity of Microsoft. Alright, so then what I'm going to do is I'm going to take this, put it all in parentheses, and we're going to divide by dt. Now, me personally, I'm just going to do 1 over dt at the beginning, so that I don't have to write a gigantic fraction with dt at the bottom. I never write straight lines properly anyway, so we'll just deal with it later. Okay, so 1 over dt multiplied by. Now, we look at this and we say, okay, we have, oops, I forgot a closed parentheses here. We have in the first set a negative 6t squared, a negative 12t dt, and oops, no, I put that parenthesis in the wrong place. It's fine. And a minus 6 dt squared. All right, next bit was a plus 12t plus 12 dt plus 7. Minus 6t squared minus 12t minus 7. All right, you notice we have a plus 7 here and a minus 7 there. Well, guess what? Those are 0. We have a negative 6t squared here, and nope, sorry, that's a positive. Man. From above, right? We got a positive 6t squared at the front, at the back end, and a negative 6t squared at the front end. And so these two things combine, and they're 0. And we've also got a negative 12t here and a positive 12t here. Now this is no coincidence, right? These are the original pieces from the original function that we had. They're all just subtracting out all the stuff that is in the f of t plus dt. So we got this 1 over dt thing. And now what's left is all the stuff I haven't circled. So negative 12t dt minus 6 dt squared plus 12 dt. All right, that's all that's left after all those other things get subtracted out. You notice that all of them have a dt in them. Now, back in Newton's day, he would have said, like, okay, well, the t squared bit, the dt squared bit, has a significantly smaller value than our dt bit if we let dt be small numbers. And since what we're trying to do is get a secant line that is as close as humanly possible to having our 2 points be on top of each other, then what we're trying to do is make dt become practically 0. It should shrink down to nothing. So back in their day, they were making kind of arguments about how it would work, and they talked about it quite a bit. For us, we prefer a little slightly different method. We prefer to use the algebra that's here. So you notice that all of our terms have a dt in it. So we could just factor it out. There's still 1 dt attached to the negative 6 in the middle, but all the rest of the terms, our dt's have been factored away from. And then at the front we have dt over dt, which is just 1. So the slope of the secant line is going to be given by the equation over there. Slope of the secant is negative 12t minus 6 dt plus 12. So what that's saying is the slope of the secant line depends on where your t value is and how far away do you want your second point to be from your first one. Now in the case of the original one up there, the distance was 5/4. We said it was going to be a distance from -1/4 to +1. So we got a distance of 5/4. We could actually just plug that in down here. Our original t value was -1/4. So for t equals -1/4. And for dt being equal to +5/4, we get that the slope of the secant line with those particular constraints is going to be -12, t is -1/4, minus 6 times dt is 5/4 plus 12. Okay, this is -12 times -1/4 is going to be a +3. A -6 times 5/4 is going to be a -30/4 or a -15/2 plus 12. This is going to be 3 plus 12 is 15 minus 15 halves. All right, 15 minus 15 halves, it's half of it, so we're going to end up with half of 15, which is 7.5. So we can verify that, yeah, this is going to give us the same thing, regardless of how we formulate this. If we want it to be, here's our initial point, and here's the distance that we're traveling, right? Now we've got a formula for it. We can set it up. We don't even have to do any more work, really. We already did the work. It's right here. So you want to give me another point to start from and then a distance away to go? We can do that. You want to pick a point and then have a negative distance? We can do that too. This doesn't create any problems. This is just a linear function now. Makes it super easy to work with. There's also something that really is awesome that we can look at right now, which is our goal, remember, was to try to get something where our 2 points were essentially sitting on top of each other, such that we were no longer looking at trying to find a secant between 2 points on this curve, but rather a tangent line that only strikes this curve once at the single point that we were looking at from before. We want to know, could we find a tangent line that would give us the velocity at this particular point, at this one particular point. So this is the tangent line at t1, x1. So down here we can get a tangent line. M tangent when dt is equal to 0. And we can get that here. M tangent is going to be equal to -12t minus 6 times 0 plus 12. The slope of the tangent line for this entire function is equal to -12t plus 12. So what is it at that one particular point we were looking at? Well, when t1 is equal to -1/4, that's the only piece of information we need now. So the slope of the tangent line at this particular location is going to be -12 times -1/4 plus 12. This got us here. -12 times -1/4 is going to be a +3 plus 12 is 15. So the object is traveling at 15 meters per second when our time is -1/4. We have this here. Our slope is the velocity of this thing. Alright, that's maybe going a little far afield, but nonetheless. That's probably jumping the gun into several sections ahead. Okay, so if we want to look at this a little bit easier and say like, okay, let's back up here, Obi, and talk about like let's talk about limits. Because also, this is another way to get into this exact same place. So, when you're talking limit, okay, your limit is basically, this is not a great definition, but nonetheless, basically what the value of the expression is approaching, regardless of the instantaneous values that might be nearby. All right, what do I mean by this? Well, if we were to try to say, I want to know what e to the infinity is. This by itself is not a particularly nice mathematical expression. So the notation doesn't really allow for evaluation of this value, e to the infinity. It doesn't really make any sense. However, we do know that if you were to select larger and larger and larger values to put into this expression, so e to the 1,000th compared to e to the 1 times 10 to the 6th, 1 million, or we compare that to e to the 1, 10 to the 10 to the 10th, right? These numbers would be ridiculously large. And there's more that we could then keep doing for this to try to get numbers that are bigger and bigger and bigger to try to approach infinity. right, 1 second here. Alright, so sorry for ads. I don't usually do it on math nights especially, but you know, I figured we could drop the pre-roll and you know, support stream. I was also going to be off for a minute anyway, saying goodnight to my spouse, so you know. Might as well, I suppose. Okay. So this doesn't really allow for evaluation of this particular thing, e to the infinity. It doesn't really make any sense. But if we find values that are ever closer to infinity, so again, e to the 1000, e to the 1 millionth, and e to the 10 to the 10 to the 10, or e to the e, or whatever you want to do. All these values are going to be closer to infinity. And then what does that do to the value of the expression? Well, e to the 1000 is very large, e to the 1 million is much larger, and e to the 10 to the 10 to the 10th is going to be much larger. And when we look at that, this tells us that e to the infinity is really going to end up being infinity itself. Right? So the way that we express this is we say that the limit as x goes to infinity of e to the x is going to be infinity. So this is also a way that we have described end behavior in pre-calculus. Although maybe, you know, your teacher did not use actual limit notation, I generally do with my pre-calculus classes because I can sort of trust them that even if they don't get it, it doesn't matter, because unless they're going on to calculus, they're not going to need it. It's just nice to sort of put pieces together and say, this is how you mathematician types work. So what we can do is we say, okay, if we wanted to know, for instance, what is the limit as x goes to infinity of the function 3x squared minus 7x plus 1 divided by 5x squared plus 50,000x minus 6 times 10 to the 10 to the 10th power. This may be a mistake, but I like it anyway. Okay, so what we want to do is say, as x goes to positive infinity, what are the values of, or what is the ratio of the values of these polynomials going to end up being? What is the ratio, no, what is the value of the rational function going to be? So as x goes to infinity, we're going to say here, okay, let's pick a really big number. So I usually like something like 1 billion. Okay, so if we were to go like this and say, okay, what is x? What is g of x? Right, 1 times 10 to the 9th, 1 billion. Okay, this is going to end up being 3 times 1 times 10 to the 9th, parentheses squared, minus 7 times 1 times 10 to the 9th. In fact, I can just write 10 to the 9th, it's fine. Plus 1. All divided by 5 times 10 to the 9th squared plus 50,000 10 to the 9th minus 6 times 10 to the 10 to the 10th. Okay, now in this particular case, if we look up top, we could say here, this is going to end up being, okay, let's just do out at least part of this. This is going to end up being 3 times, now 1 times 10 to the 9th, or just 10 to the 9th squared, is going to be 10 to the twice as many tens all multiplied together, right? We're squaring it, so it's that thing times itself. 10 to the 9th times 10 to the 9th. So it's going to be 10 to the 18th minus 7 times 10 to the 9th plus 1 over. Same thing on the bottom. 5 times 10 to the 18th plus, now 50,000 is also 5 times 10 to the 4th and then we're multiplying by 10 to the 9th, and when we combine these 10 powers by multiplication, their exponents get added together. So this is going to be 5 times 10 to the 13th power minus 6 times 10 to the 10 to the 10. Now, just for the top stuff, when we look at this, right, what's going to win? What's going to take over the, like, driving of this value? Well, right, this is 3 times 10 to the 18th is a 3 followed by 18 zeros. Right, that's that number. And then we're going to subtract a 7 followed by 9 zeros. And then we're going to add 1. Right, so again, what's going to win here, right? Right, it's that leading coefficient. The 3 is really what's going to matter. subtracting, 7 with half as many zeros is just infinitesimally smaller. It's going to make no difference whatsoever. One of my favorite examples of things to do is to go like this and say, okay, here's a 0. Here's 1 times 10 to the 9th. There's a billion, right? Or in fact, I don't even write this. I just say a billion. Okay, now where along this spectrum is a million? Oops, that's off the... Oh well. I mean, surely, like, a billion and a million, right? They're words-wise, they're right next to each other. So a lot of people will be like, okay, well, like a million is probably going to be like about halfway? Right? What do you think? I often put this up on the board and just like let everybody guess a location. Yeah. Mm-hmm. Yeah, 500 million is halfway. Well, that means it's 1/500th of that distance, or 1/1000th of the full distance. So, like, 1/1000th is about here, and that's probably too far. I mean, that, like, that just blows people's minds because they're like, oh my god. But part of the reason that that happens is that we are sort of geared toward having a logarithmic mind. So that a million is, roughly speaking, a third of the way, or 2/3 the way to a billion. Because this is, again, 1 times 10 to the 6th. This is 1 times 10 to the 9th. And if 0, if we just picked 1 instead, right, 1 times 10 to the 0, well, 0 zeros, 6 zeros, 9 zeros, right? It's 2/3 the way there, so there you go. That's too far, but anyway. Picking a value that's approximately 2/3 is actually something that our minds are kind of geared toward doing. Although most people flip it the other way and make it only a third of the way or something like that. Anyway. So yeah, this is really what they're talking about degrees of smallness. Is like, these other numbers are completely irrelevant in terms of what's going to happen as x goes to infinity. All right, similarly here with the 10 to the 18th and 10 to the 13th, like, that's not that far apart. It's only 5 zeros apart, but it's still a tremendous difference. And so this is not going to matter at all either. Now this thing, I don't even know exactly how many zeros that is. 10 to the 10th, right? So that's 1 followed by 10 zeros is 10 billion. So this is a -6 followed by 10 billion zeros. So, she big. So this number actually does win for this particular setup. But that's the thing, is that when we're talking about infinity, this is peanuts, right? This is nothing. Take that number and raise it to the 10th to the 10th to the 10th. Right? So if x is 10 to the 10 to the 10 to the 10 to the 10, right? Now do the exact same experiment. All right, well, now we've got 3 times 10 to the 10 to the 10 to the 10 to the 10 parentheses squared minus 7 times 10 to the 10 to the 10 to the 10 to the 10 plus 1 and then down here 5 times 10 to the 10 to the 10 to the 10 to the 10 parentheses squared plus 50,000. Yeah, well, 10 to 10 to 10 to 10 to the 10th minus 6 times 10 to the 10 to the 10th. Okay, so now if we look at all this, again, these are going to have twice as many zeros as these things. So these things are irrelevant. Your 1 here is irrelevant. And the 10 to the 10 to the 10 has fewer powers of 10 by a significant amount. So again, it's irrelevant compared to the other two things, which have the same value or have the same number of zeros attached to them. So all of this, as x is going to infinity, is getting closer and closer and closer to just 3/5. Right? The degrees of, in this case, the degrees of largeness are exacerbated by our exponents. So if we have squares, it makes it so much larger than something else. In the case of something that's small, it's the opposite case, right? If you have something that's incredibly small and you square it, then it becomes incredibly much more small. So here the limit of g of x as x goes to infinity is going to be 3/5. All right, so next question, is this helping at all? So this is kind of explaining the concept behind it, but it's not necessarily, okay. Oh, good. It's explaining the concept behind it, but it's not necessarily hitting the exact same notes that is. Again, we teach things a little bit differently, both just at my 2-year college and also because it's been 100 years since this thing was written. So... Hey, Killer King. So the thing we just did with the rational function, I would consider pre-calculus. So I wouldn't say that it's not a good source, but what you have to remind yourself of is that this is an old book. And so it's not necessarily up to date. Granted, again, right? The concepts are the same, but the overall feel of the book may very well feel like a foreign language because, again, it's 100 years old, and it could work. It could be fine, but you may want to supplement it with something else. So we use the OpenStax book. I find it is fine. It may not be like the most perfect thing ever, but it's, you know, it does the job. and it uses the more recent, language. Man, you really want me to get into computer science. All right, so that's our OpenStax Calc 1 book. If you are looking to actually spend money, you could go with something like the Stewart Calc 1. Stewart Calc 1 book, which I would not pay more than probably $20. So you can find an old edition on eBay, something like that, which are just fine. Like they're not the most up-to-date version, but who cares? The publishers are just making a whole bunch of money off of it. Yeah, my spouse is a computer scientist. I'm not. I only took C. Your nap today, you were dreaming of explaining density of planets in the solar system, and yesterday you were dreaming about helping a colleague with calc, or were you actually? Interesting distinction between the two. All right, so we want the dreaming. Yep. Huffman code is a particular type of optimal prefix code that is commonly used for lossless data compression. Okay, so I have seen something like this, but I would not say that I necessarily have done any work with it. I've definitely not done any work with it. It's fine. Oh. Technique works by creating a binary tree of nodes. These can be stored in a regular array, the size of which depends on the number of symbols n. Node can either be leaf or internal. Okay. Oh, goodness. No, my spouse does not teach. She, once upon a time, was working in our math center at the University of New Hampshire. And so she was a student aide as a math major. Which is really too bad. I should have applied to work there at some point, because like that would have been really cool. I instead worked at the AV services department in underneath our library and hauled stuff around campus to hauled stuff around campus to set up things for other teachers who did not know necessarily how to work the AV systems. Like they knew how to get their computers working, but they couldn't necessarily interface. There were a couple of really fun ones. It really depends on how good at programming you are. If you're like supremely good at programming, it's probably because you have a firm grasp on everything else. That was actually one of the things that we were discussing as physics majors, was on our like first day that we visited the campus. Our advisor, stood up, the program head stood at the front of the auditorium and was like, and if you have a physics degree, you can get a job pretty much anywhere, because people with physics degrees are always in demand and things like that. And I was kind of like, oh, that's nice. And then years later, I found out that it's pretty much the same is true for math degrees, especially applied math. Like, you can pretty much get a job anywhere you want. What you've got to do is apply yourself and actually look at what it is that you're doing, and then try to have a goal in mind. In my data entry job, my goal was to get as much done as I possibly could, so that I didn't have to use all my brain power doing this mind-numbing, stupid data entry that I hated. So instead, I spent 30 hours, so my entire week, 1 week, programming in Visual Basic to literally do my job for me. It took 30 hours, and I was inside the shell, inside our little internal Visual Basic program, the prod thing that we had going on. And the key was that I would have it go into an insurance provider, individual person. It would go into their provider file. It would read all of their affiliations, so every company they worked for, and it would pull all of their numbers and then put them into an array. And then it would create a second array and go into the first file and copy all of the tax affiliations that company had, and then copy them all into an array, and then go back to the provider's file and enter them all in. And then it would go back to the second company that they worked for and copy all of those tax affiliations into the second array, overwrite everything. I think it eventually, I made sure it deleted it so that it wouldn't have hanging terms that would try to enter again that didn't work. That took an afternoon. So it would go into the second company, create a new array, pull all of those tax affiliations and enter them into the provider's file. This would sometimes, doing it by hand, just entering tax affiliations, would take 2 hours for one person. And that was the moment that I said, okay, screw this. This is not worth my time. And not to mention, I'm making errors. I had 2 windows open so that I could copy everything over here and then enter everything over here. And it just, generally speaking, it was not fun. And then, the one I was reading from would time out because I'd been sitting there a long time. And then I'd have to log back in. It was just such a pain. I was like, this is not fun. And so I programmed Visual Basic to have it do my job for me, and it shrunk the largest of the files, which again took me 2 hours to do by hand, took my program 5 minutes at most, with many of the provider's files being done in less than 1 minute, when it would take me, a few minutes to do them. I told my boss what I was doing, and this was, on Friday. I said, "All right, I've done it." And she was like, "What did you do?" I was like, just trust me. My numbers were a little bit down this week, but I've got it." And she was like, "Okay." So I run it all day Monday. Come back after the weekend, run it all day Monday. I had run it like maybe a quarter of the day Friday and was debugging. And ran it all day Monday. On Tuesday morning, she shows up to my desk, slams this big pile of paper down, and she goes, "What did you do?" I just sat there smiling like, oh, just you wait. So I showed her exactly what I had done, and it wasn't, I wasn't cheating the system, which is I think what she thought I was doing, like, telling it to enter stuff and then delete stuff and enter stuff again or something like that. Because my numbers were off the chart. So I had done, thousands of data entry items instead of dozens to 100. So I showed her what I did, and she showed a few other people, higher up, some of whom actually understood what was going on, and like said, here's what the numbers are, here's what's actually happening, and yes, we can audit this whole thing, and actually, he's actually doing his job. So they ended up sending me a $500 bonus, and a letter from the president that was, president of the company. It was like, "Hey, you're doing great things, thank you." I was like, "All right, cool." I'm leaving in 2 months. So I basically ran it on this project for, the whole rest of the 2 months that I was there. This guy that was a friend of mine who had taught me, occasionally I get stuck, and I was like, "Hey, Dave, what's the code I'm looking for here?" And he'd just shout it back over the cubicle. "All right, thanks." But he sat with me for probably a few hours on day one, trying to get the structure of Visual Basic, because I'd never programmed in Visual Basic before. But I was like, "Okay, so this is what I'm doing," and he's like, "Yeah." And so probably after about 2 hours, I was just like, "All right, I got it." Thank you, sir. So yes, because I understand math, programming is easier, but at the same time, like, I had to work at that first. I had to make sure that I understood C. And once I understood C, all the rest of them were fairly easy to be able to pick up. So again, I've edited C++ and C#. I have written from blank in MATLAB, Python, and Perl. I have written from blank in HTML. And there are probably a couple more that I've edited or done something else with, but Python's really cool. I like it. And I wish it was a little more math friendly, but whatever. As soon as you get the NumPy library, it's okay. And there's something else. Oh, like TI. I can do TI language. That one's pretty easy. Input output, not assembly. Now, the guys who can program TI assembly, they're nuts. They did really awesome things. Math bits. I don't necessarily know what that is. Mathematics and computer programming. if you're looking at the actual like math bits, like web page, yeah, I haven't poked around this website at all, but that could be interesting. Alright, so Blainland, to get back to your original question, what is the topological sort algorithm? That's fun. So if you have a linear, nope, if you have a directed graph, you'll create an array that returns the nodes with either zeros or ones, looks like, depending on whether or not it's connected in that direction. So like the position 1, 2 would have a 1 if 1 goes to 2. If 2 goes to 1, then the position 1 to 2 would be 0, but 2 to 1 would be 1. Now in theory, you've also got a in theory, nope. You could have something that goes back and forth in both directions. Okay, so if you had like 1 goes to 1 and 5, 5 goes to 2, 6 goes to 2 and 3, 7 goes to 5 and 6 and 4, 3 goes to 7 and 4 goes to 3. Then your topological sort would be like, all right, 1, 2, 3, 4, 5, 6, 7. Oops. So this is why you don't draw out the matrices until you actually 2, 3, 4, 5, 6, 7. All right, so no node ends up going to itself. I don't know whether that's oversight or a good idea. 4, 5, 6, 7. All right, so rows are going to be start and columns are going to be end. So does 1 go to 2? Yes. Does 2 go to 1? No. Does 1 go to 3? No. 4? No. 5? No. Oop, nope. Does go to 5. Jump the gun there. Doesn't go to 6, doesn't go to 7. Does 2 go to 3? No. Does 2 go anywhere? 2 does not go anywhere. Okay. 3 goes to 7. 4 goes only to 3. 5 goes to 2. 6 goes to 2 and 3. 7 goes to 4, 5, and 6. Okay, so this would be, as far as I can tell, this is going to get you the array, which shows you which nodes point to which other nodes. Again, as far as I know, this is how it would work. That is definitely not what the output is coming up with in this example I'm looking at. Identify a node has no in degree, no incoming edges, and select that node as a source node of the graph. Okay. Delete the source node with 0 in degree, and also delete all outgoing edges from its graph. Insert the deleted vertex in the result array. Update the in degree of adjacent nodes. All right, so not really. This actually can help you, but yeah, this can help. Okay, so select element with no in edges. So something that ends at 1, or rather doesn't end at 1. This never ends at 1. So with this, that's going to tell us that this is going to be the source node. Now, there could be other places that also do this, but the fact that I just did this, Delete the source node with 0 in degree, and also delete all of its outgoing edges from the graph. So we're going to delete this column, and we're also going to delete this row. Okay, and then there isn't another one that's here. The resulting array at the end of a process is called repeat steps 1 to 3 until the graph is empty. Okay, so in this particular case, this looks like it is a cyclic graph. Yeah, 3, 4, 7 is a cycle, and so that causes a problem. 7, 6, 3 is also a cycle, so that causes a problem too. So there is no topological ordering for this particular graph due to that. All we'd have to do, though, is get rid of one of the nodes that starts at 7, maybe multiple, and make sure that there isn't a graph, or make sure there isn't a cycle. Actually, 3 to 7 might be the one to get rid of. So if we take this out, right, start 3, end 7, then now we do have another one, right, 7 and 3 here. So 1, then 7 becomes the source node after that. Oops, not 3. Don't delete 3. The source node is 7, so then afterward delete 7. And then what source nodes do we have? We have 4 and 5 and 6 are all now source nodes. So at this point, because they're all the same, how many incoming do they have, right? All you're really doing is summing the columns to determine what that is. Yeah, okay. It's possible to return multiple topological sorts given that you might have more than one node that is a 0. So at this point, right, after 1 and 7, like 4, 5, and 6 all have 0 in nodes. And then once you eliminate them, 2 and 3 are going to also have no in nodes, and they're disconnected from each other. So it doesn't really matter how you order them. Maybe like if there are some that are tied, you just do them as numerical order. So whatever you come across first as you're counting. Yeah, that's kind of interesting. All right. Who else has questions? slowing down here, let's grab an example out of our Kreyszig book. We were looking at linear algebra last time. Or at least, that's the page I was on when I got distracted. We ended up not doing anything out of the Kreyszig book. Node pointers. Structured variable or object containing at least one field whose type is a pointer type. Okay. Yeah, I'm not really. Like, nodes are pointer types. So. Again, not really my specialty. Alright, there's a certain Markov process that has initial state 1, 1. And no, that's not A. It's X, for example. And the transition matrix so the thing we're multiplying by between each stage in the process ends up looking like a half, 3/10, half, and 7/10. Alright, so find the next three vectors x sub I in the process. So what we get here is that x sub 1 is going to be equal to a times x sub 0. Just going to be a half, 3/10, 7/10. Yeah, no, okay, we're good. Multiply by here, 1, 1. With matrix multiplication, we are going to multiply this row by this column to get our first row, first column. So that's going to be 1/2 times 1 is a half, plus 3/10 times 1 is 3/10. So 1/2 and 3/10, that's 5/10, and 3/10 is 8/10, or 4/5. And then we're going to do second row, first column. To get 1/2 is 5/10 plus 7/10 is 12/10, which is 6. Yeah, 6/5. Alright, so that's x1. x2 is going to be equal to a times x1. Half, 3/10, half, 7/10. Multiply by 4/5, 6/5. So half of 4/5 is going to be 2/5, plus 3/10 times 6/5 is going to be 18/50, or 9/25. Bottom here is going to be a half of 4/5, again is 2/5, plus 7/10 of 6/5 is going to be 42/50, or 21/25. It's going to be times 5, top and bottom is 10 plus 9 is 19 25ths. And second, 10 25ths plus 21 25ths is going to be 31 25ths. No common factors. And x3 is going to equal a times x2, which is again 1/2, 3/10, 1/2, 7/10. Times 19 25ths, 31 25ths. It's going to be equal to half of 19 25ths is going to be 19 50ths, plus 3/10 of 31 25ths is going to be 93 250ths. Alright, second line, half of 19/25 is 19/50ths. Plus 7/10 times 31, 217 over 250. Just gonna make times 5, top and bottom to 19 makes 100 minus 595, plus 93 is 188. (250ths). All right, 95 250ths plus 217 is going to be 312. It's going to be 94 1/25ths. These are all out of 5, so there's nothing to do there. Half of 300 is going to be 150. And half of 12 is 6. Alright, so there's our final result after this markup process. In addition, this was A times x sub 0. So this was going to be A cubed times x sub 0. We could also let it be that particular form as well, if we felt like it. How do you make a 9 digits number shuffle algorithm? So I would say that if you're trying to do that, you want to make a list of your 9 numbers. I would say, now this could be completely, not an efficient way to do it or whatever. But what you do is you create your list of numbers that you are allowed to use. So in this case, 1 through 9, right? And then create a second like index matrix or array, which is going to allow you to say, or vector, which is going to allow you to say, can we use each of these numbers? So originally it would be set to all ones or all zeros if you want to say, I have used this number to be 1. So set it all to, I would say set it all to ones to say, is this number available? And then you say, if if the number is available, so there's a few different ways you could do this. You could say, like, if the number is available, you could return the index of all of the ones into a separate pile and then pick a number out of that at random and then backtrack as to which one it is and then switch the ones to zeros as you pick those particular numbers. And eventually you've only got one left and then that's it. You could do a few other things, I guess, but Fisher Yates, I have no idea what that is. I would say that that is fairly efficient, yes. Because all it's doing is, are we switching numbers? So what's in the what's in your last one is going to say, like, okay, pick a number at random for all of our indices, and whatever the index is that you select, whatever your index is that's selected at random, you're going to swap your 5th position one with whatever that is. I would say that's very efficient, yes. And then you work your way backwards. Or you could start at the beginning and then work your way forward. It obviously doesn't matter. So you could do whatever you want there. I'm not going to say it's the best, but it looks very efficient. You could probably make the argument that it's not the best, but you'd have to have something else that works in somehow less computer time than N. Alright, gonna put up last call here. So, anybody have anything they want to talk about real quick? Otherwise, had to? What do you mean had to? I didn't do particularly well in I didn't do particularly well in matrix theory because I was putting all of my attention, despite the fact that it was a fairly easy class. I had to put all my attention into my partial differential equations class, which I got an A in, but it was very difficult to go the other way. Be like, I'm just gonna focus all my energy into this one. It was maybe not a good idea. Alright, who we got? Selena's playing Soma, that's always fun. Yeah, let's go see Selena tonight. So she's playing Soma. If you've never seen Soma, maybe now's a good time to back out. But we played it here on this stream, and it was pretty intense. She's pretty close to the end, so like if you don't want to necessarily give yourself spoilers, you know, I don't blame you. It's alright. But I hope you all have a good rest of your week. Gonna head out here. We're going to come back on Friday for more, probably Planet of Lana again. Hopefully it will stop breaking, but we'll see. I just need to stop alt tapping. It's fine. But I hope you all have a good rest of your week. Let me know if there's anything you want to talk about next time, and we'll see you on Friday for gaming or next Tuesday for math stuff. Hope you all have a good night. This is Obi-Wan Pez for N Simplex Pachinko. Have a good one.